In this video, I'd like to introduce you to a type of first-order differential equation that we call autonomous equations. Now, the word autonomous generally has the feeling or the meaning of sort of self-contained. When you do autonomous navigation for robots or lunar rovers or whatever, they're navigating on their own. They're not going from someone else. So the autonomous means like sort of by themselves. And for autonomous equations, um, first order differential equations are generally can be written in the form of y prime equals some function of t and y. Separable differential equations, you had a function of y times a function of t. Well, in autonomous equations, it's just y prime is a function of y alone. There's no t's involved here. So the derivative of the function is related only to itself. It's only a function of y. I'll note that this is a separable equation. Every autonomous equation is separable because I can just divide both sides by that f of y and multiply both sides by dt, and you've got it separated. It's just a matter of integrating both sides and solving for y. Okay. Now, how you do that integral, of course, depends on what the function is that you have. Now, the most basic example of an autonomous equation is just y prime equals y. This is one we've looked at before. It's your basic exponential growth. Solutions are all of the form y equals c e to the t. Graphing a few of those solutions, I can see these here. Now, one of the things I need to point out is that because the derivative of y is not dependent on t or x, I almost said x, but x and t are interchangeable, right? When you draw a slope field, it's really easy to do because you can just figure out what's going on with respect to y. Nothing changes with respect to x. So if you've figured out you need a particular slope right here, then that's going to be the same slope there and there and there and there and there, and that for every value of x it's the same once you know what's happening for one value of y. So I notice on these curves, right, the slope here is the same as the slope there is the same as the slope there. Right? In fact, each one of these curves is just a translation of the other curves. Now, it seems a little funny because the effect here of the c should be a scale factor in the y direction, right? So the black curve is c equals 1. That's just y equals e to the t. The red curve is with c equal to 2. So it's scaled up by a factor of 2. But because of the algebra of exponentials, if you think of this as 2, the red curve is 2e to the c, the 2 could be written as e to the log of 2. E to the log of 2, yes. So e to the log of 2 times e to the t is actually e to the t plus log 2, natural log 2. So that's a shift in the t direction to the left of log 2. So the red curve here, although it is scaled up by a factor of 2, it is also a shift to the left by natural log 2. And every one of these curves, every one of these solution curves is just a shift from another one. Now granted, with positive c's, they're all going uphill, and with negative c's, with c negative there, these are the ones headed downhill, and certainly the ones down below are not shifts of the ones up above, but all of the ones down below are shifted of all the other ones down below. Okay. Notice there's one very special solution here too, is when c is equal to 0, it's just the x-axis, y equals 0. Which actually is interesting because with y equals 0, the constant function y equals 0, the derivative of a constant function is also 0. So the derivative is always 0, the function is always 0. That's clearly a solution to that equation. But it shows up in the set here. This is the general solution. That is a linear, that's first order linear as well. So I know that this is a general solution here. And c equals 0 gives me that one special solution. Now let's take a look at another one, and I want to talk about how I analyze these things. Without actually solving them, I can know a lot about what the solution curves look like. And here's how we're going to do that. So let's take a look at this. Y prime equals y squared minus 4y. And the first thing I have here is the associated slope field. Now all I did was I went into WAMAP and asked it to draw me a graph of a slope field, and this is what it gave me. But I claim I can figure this out myself in the following manner. So I'm going to factor a y out of that. So it looks like y prime equals y minus 4. And I noticed that those two factors would give me zeros with y is equal to 0 or y is equal to 4. Those two particular values of y are what are called equilibrium values. Notice in the thing up here that at y equals 4, all of the little hash marks are horizontal. That is, y equals 4, the constant function y equals 4, is a solution to this differential equation. Because if you plug the y equals 4 in on the right-hand side, that's going to make this factor equal to 0, so the whole thing is going to be 0. But the derivative of that constant function is 0. So 0 is equal to 0. Y equals 4 is a solution to that differential equation, and you can see that right there. It's called an equilibrium value because from the point of view of the independent variable being time, if you're at a y value of 4, you will stay at a y value of 4 forever because the function does not leave it at that point. The solution curve, y equals 4, is just constant. It stays 4. Likewise, y equals 0 is also an equilibrium value because I see here all these little hash marks along that line are all horizontal. And so y equals 0, again, a constant function, the derivative is equal to 0. So left-hand side is equal to 0. Plugging a 0 in here, y equals 0. Makes the right-hand side 0, and so yeah, they're equal to each other. And as time passes, your y value would stay at 0. It stays there. It's in equilibrium. Okay. Now I claim that I can draw this graph, this slope field, without asking for help from a computer, and here's what I do. Using those two equilibrium values, I draw the graph of this function right here. So the vertical axis here is the y prime axis, and the horizontal axis is the y axis. Okay, so I'm thinking of y as my input variable, and y prime is my output variable, looking at that equation. Well, this is a quadratic equation to y. I've got it factored so I can see the intercepts. Y equals 0 is an intercept, and y equals 4 is an intercept. And it's an upward opening parabola. So it starts up here, goes down, and it goes back up again. Now, how far down we could find out, but anyway. But in general, I would just know, oh, it's an upward opening parabola. Halfway in between those 2 points would be where the vertex is. I could take that, plug it in, and see, what it is. But what I see here is that I see for values of y less than 0, y prime is positive. So notice on these down here on this graph that we had there, for the negative y values, these are all positive sloping little hash marks that the slope is going uphill. The closer you are to 0, the closer this is to flat, right? Because where is it right here? At 0, the slope is 0. Move away a little bit, you got positive slope, but still pretty small. Move away further, you've got positive slope, but getting bigger. So the further away from 0 y is, the steeper these hash marks are. In fact, it's pretty hard to tell any difference between this one and that one. But certainly you can see that this one is not as steep as that one, which is not as steep as this one. Right? So the further I get away from 0, the further this gets away from 0, the bigger this gets. So the steeper these hash marks have to be. Okay? Likewise now, in between 0 and 4, these are all negative values. So the slope is negative in between 0 and 4. And if you look what's going on here, sure, these are all going downward in between y equals 0 and y equals 4. They're starting off close to slope 0, getting steeper and steeper as I go up until I get to 2. At y equals 2, you're as steeply negative sloped as possible. Whoops, I'm pointing to something off the screen. At y equals 2, your slope here should be negative 4, right? So on this graph at 2, these little hash marks along y equals 2 are all negative slope, negative 4. And then getting closer to, still negative slope, but closer to 0 slope again as I go up. And I get back to a 0 when I'm at 4. Now, above y equals 4, the slopes get positive again. And so up here, I have positive slopes, starting off with small positive slopes, getting steeper and steeper as you go upwards. Okay? So this little graph right here, this graph of this quadratic, is telling me what the slopes need to be in my slope field. And because this does not depend on x, as soon as you know what's happening along the y-axis there, it's the same thing that happens to the left and to the right. Just keep the same slope going all the way across. So we can even begin to see what the solution curves look like. I can see that if I had an initial value in here somewhere, that this graph would be headed downhill, and then it would have to start flattening out and maybe approach that horizontal asymptote. I don't think it wouldn't be able to cross through that, because if you ever hit it, you'd just stay on it. So my guess is it comes down and uses that as a horizontal asymptote. And in the other direction, it's going to do the same thing going that way, right? So I'm going to have this horizontal asymptote along here, and then it'll come down and go across. If my initial condition was down below, it looks like I'm coming up and then approaching that horizontal asymptote. Likewise, if my initial condition was up above, I'd have this horizontal going this way and then headed uphill. So that's what I'm expecting. I will draw a few of those here. So here's those things. So I have this plotted, 3 curves where the initial condition is somewhere between, the y value of the initial condition is somewhere between 0 and 4. 2 of them plotted with initial conditions with y less than 0, and 2 of them plotted with y bigger than 4, and you can see the shape of those curves. Now those 2 equilibrium values, 0 and 4, have 2 different flavors to them, and one of them is called a stable equilibrium, and one of them is called unstable equilibrium. So 0 is the stable equilibrium, in that if your y value is a little bit away from 0, over time it'll be pulled back down to 0, because that's the way things are going. 4, on the other hand, if your y value is a little bit off of 4, either above or below, the curve will pull away from 4. I picture that this way. I'm going to balance this, I'm going to attempt to balance this pen on my hand. There is a stable point, if I could stay still, pointing straight up. It's technically possible to balance this pen pointing straight up, but it's such an unstable equilibrium point that it's really hard to do. Okay. There's another way I can balance this pen on my hand, and that's this way. It's balanced. This is what I would call a stable equilibrium point, because if I perturb it from that, it just gets pulled back down to that position, right? So this position is like the 0 on here, or if you start away from it, it'll be pulled back to it, where the 4 is like this position, where if you're not right on 4, it's not going to stay there, okay? So equilibrium values, there's stable, there's unstable, and there's also a thing called semi-stable, which we'll take a look at in the next video. Okay. Now, I did happen to do the calculation to solve the differential equation. We will show you how to do that in a separate video. But one thing I want to point out here is that this was not linear, and that this is not actually the general solution, because although it does get the y equals 4 solution when c happens to be 0, it does not ever give you the y equals 0 solution. There isn't a value of c you can plug in here to get the y equals 0 solution. So, but I can see that y equals 0 has to be a solution, because I saw the factors here, and y equals 0 is one of those values that would make that work. Okay. One last thing I want to say in a minute is that although we have it written this way, if you think about this a little differently, take the reciprocal of both sides. Instead of dy dt equals f of y, you could have dt dy equals 1 over f of y. So you'd have t, think of t as a function of y rather than the other way around. And I'm just telling you the derivative of t is equal to this, and you can just integrate it. And so you'd get the antiderivative plus c, and all of the solutions would just be looking the same but shifted in the t direction, which is precisely what we saw up here and here. Every single solution looks like another one shifted over. Okay. All right, we'll have to do some more examples in the next video.